Welcome to Study Loop.
Okay, so for this problem, you have two protons being launched at another that are several meters apart at high speeds, and then the question is, what's the force that they exert on one another? And so a couple of things. So you might look at this problem and be like, what's the formula that relates force to their initial velocity? And maybe there is some, but if you're wondering, like, where is that formula? It doesn't exist. One philosophy I like to take with problems, and I will take some time to wax philosophy for the intro problems because they're a little shorter, is like, what can you learn? And usually, if you can imagine what can you learn, it'll usually take you to where you want to go faster, maybe, than you would think. At least you've played around with the problem a bit and sort of connected some ideas in your brain. And so, what can you find out if they're going at each other? You know how fast they're going. You can find how close they're going, as you may have seen in problem 5. And so, yeah, and then the second major point I wanted to make at this problem was that they're saying that they started several meters apart. Now, first I was like, several meters apart? Can't you just say 3 meters? But I think by saying several and not a particular number, they mean, well, you can pretty much neglect it because the kinetic energy is going to be a lot larger. And then so now I guess I'll actually estimate it. So if you estimate the potential energy, let's just say that they're like 1 meter apart, then U is approximately K, so that's like 10 to the 9. Each of them has a charge of like 10 to the minus 19 because they're protons. So what's that? And if it's 1 meter, then you're just dividing it by 1. Then it's 10 to the minus 38 plus 9 is 10 to the minus 31. So that's around, right, did I do that math? Did I do that math right? No, I did. 1 second. So 38 minus 38 minus 9. Oh, oops, that's minus 29. Wow, I'm having minus 38 plus 9. Yes, that's 29. Okay. And the kinetic energy, so the mass is, if you want to compare it to the kinetic energy, the mass is around the mass of a proton, which is 10 to the minus 27. And the velocity is basically v squared, or the velocity contribution is v squared, and that's 10 to the 5 squared, so 10 to the 10. So that's 10 to the minus 17. So this is much bigger. So you can neglect any potential energy that they might have. So yeah, anyway, so now on to finding how close they get. I'll just like pictorially draw it. You want to say that you want to use energy conservation. E initials E final. Initial energy is kinetic. So it's 1/2 mv squared for each of them. So it's 2. And then the final energy is potential. So that's K, Q1, Q2, and each Q is the elementary charge unit, 1.6 times 10 to the minus 19. And then you can find R with this. So I get the formula that R is the square root of K E squared over V squared. The velocity is 10 to the minus 10, 2 times 10 to the 5. Mass is, I think, 1.67, 10 to the minus 27 kilograms. K is your 9, 10 to the 9. E is 1.6, 10 to the minus 19. And so I got that the radius was, pulling out my Mathematica sheet, 1.86 10 to the minus 6. So they're getting microns, levels of closeness. And then you can say, okay, now I know how close they are. What's the force generated? And so you're like, all right. So again, you can use force as E is K, E squared over r squared, where this is your new r. And I'm just going to double check my math on that. Like, did I actually square that? Because I remember I got a number I wasn't super excited about. It was saying only 6.68 times 10 to the minus 17 newtons. So it's pretty small. For some reason, I thought it would be bigger. But you could, of course, estimate, make other estimations, use average proton distances to get actual amounts in newtons. But I'm not going to take the time to do that because I tried